very happy to introduce our today's speaker. It is Dr. Andrea Blanco-Redondo from Nokia Bell Labs. And the title of her talk is Novel Solitons and Topological Quantum States Using Silicon Photonics. Andrea, please.
All right, thank you very much, Anton, and thank you to all of you who have organized this seminar. I'm very happy to have the chance to be talking to you. So yeah, I'm going to tell you about these two lines of research that I've been focused on the past few years. I joined Nokia Bell Labs about a year ago. Before that, I was with the University of Sydney, so you will see that many of the results that I will present today were actually initiated there. But all the things that I'm going to talk to you about is things that I still continue activity on, as you will see. So before I tell you anything else about what we've been doing, I would like to acknowledge my collaborators that I've been very fortunate to work with over the last few years. And it's a long list, but I wanted to highlight these folks here with the pictures, the people that have worked with me in the soliton work over the last few years, and also the people that have been quite instrumental in the topological quantum work. You have them here in the pictures. Especially, perhaps I'd like to acknowledge Dr. Anton Samusev, who's a postdoctoral fellow at the University of Sydney, and he's taken some of the latest measurements that you will see in the soliton, pure-quartic soliton laser work that I'll tell you about. And I would also like to acknowledge Mihail and Cooper, who were my former students in Sydney, that have taken some of the latest measurements in the topological quantum photonics line. So just a few words about where I work at the moment. So I work for Nokia Bell Labs in New Jersey in the US, and we have two main locations in New Jersey, and I just wanted to say a few words about them because they're both quite special. So right now my laboratory is in Crawford Hill in Homedale, which is about 45 minutes south of Manhattan, as you can see here. And this is a very special place in the middle of the forest, basically, in the middle of a very foresty area, which is famous for like some inventions. For example, optical tweezers were invented here. But perhaps the coolest thing about this building is that it's home to the horn antenna with which cosmic background microwave radiation was discovered. So the first evidence of the Big Bang. But as I was mentioning before to some of you who connected earlier to the call, we're moving to a different lab. We're moving to the Bell Labs headquarters that are in Murray Hill, only 30 minutes away from Manhattan. And again, many things have been invented in this building, but perhaps I'm just going to highlight one because it's so important that it really changed things tremendously, which was the invention of the first transistor. So it's a pretty cool building to be moving in. Because the things that I will tell you about are actually relatively fundamental, or let's say they have a relatively long term application horizon. I wanted to mention that this is just a small subset of the things that we do in the silicon photonics team at Nokia Bell Labs. We do things that are not as fundamental as the things that I will tell you about before. We work on all the problems that have basically a shorter term application horizon in fields like data centers, optical communications, and computing, right? Like compact silicon photonic modulators for coherent communications, tunable lasers, also for optical networks, tunable like silicon integrated tunable lasers, and optimized passive silicon components. So I just wanted to give you the idea that what we do in our department is much bigger than what I will tell you about today, and that many of the things that we do there are, way more, not more applied, but like more applicable in a shorter term horizon. All right, so with this, I want to delve into the kind of things that I will be telling you about today. And I wanted to divide this talk in two lines, right? So one is nonlinear effects and novel soliton physics, and the other one is topological quantum photonics. Now, these two lines actually have underlying physics that connect them both, and in particular, there's a very strong component of very careful engineering of the band structure of the dispersion relation in both cases. So that's actually why I worked on the two of them. But they have very different goals. So I really wanted to separate the two so that, you know, it doesn't create any confusion. So I'm going to start by telling you about new types of solitons that we've been investigating lately and the technologies that may be derived from them. So just as a matter of an introduction, I'm sure you all know what solitons are. They are like wave packets that propagate and change for very long distances, and this is because of a very careful balance of dispersion and nonlinearity. They were first discovered in water, and they've been discovered in many other fields of physics, and they've been observed in many other fields of physics. But perhaps what's more relevant to us is the first observation of optical solitons and optical fibers that was actually coincidentally done at Bell Labs by these three gentlemen here. And what I wanted to show you, this is an image of the first paper, that's why it's so kind of blurry. But I guess the idea that you can see here, just with these three measurements, it shows you how soliton physics manifests in optical experiments, right? So when you do experiments at low powers, you basically have dispersion dominating the propagation. So your pulse is broad in time because of the effect of the different frequencies traveling at different speeds. When you hit a point in which nonlinearity and dispersion compensate each other, then you have a pulse that keeps its shape in time, and it propagates unchanged. This is what we call soliton shape preservation. And finally, when you increase the power to a level in which the nonlinear effects kind of dominate over the dispersion, you get what is called higher order solitons, which basically at some point they manifest as soliton compression. It's a soliton that breathes. It's basically, it can be interpreted as a state of several solitons that are bound to each other, and they breathe, and at some point you get soliton compression. So these two things are signatures that we use to identify soliton propagation. One is shape preservation for long distances, and the other one is soliton compression. Okay, so initially people thought that solitons could be really interesting just to transmit information along very long optical fibers, just because if you can get a if you can get a pulse that doesn't change, that sounds pretty great to transmit information. However, it turned out that didn't really take off because of issues that arise from the nonlinear phase noise that basically render solitons kind of useless for coherent communications. But a field in which solitons have been extremely successful is the field of lasers. Now, the first laser was also coincidentally invented at Bell Labs by Olehno and Stolen. And the idea was very simple. This doesn't look anything like soliton lasers look today, but just to give you an idea, it's just a fiber cavity in which the fiber itself conforms the shape of the pulse, right? So that seems pretty great, pretty simple, and just by using the interaction of nonlinearity and dispersion in the fiber, you can get a very well-defined shape of the pulse with a fixed energy width relation. So basically the width of the pulse determines the energy of the pulse, and these pulses, when they come out of the laser, are actually unchirped. They are transform limited. So that sounds pretty good, but what is the problem here? Well, the problem is precisely this energy width scaling, right? So what I'm showing you here again is a picture from the first paper here, this paper in Optics Letters. Let me just highlight the important part because it's a very complicated graph. Otherwise, what we have here is the peak power as a function of the inverse of the pulse duration. So as you can see, if you think in terms of energy rather than peak power, the energy scales as 1 over the pulse duration, right? So what this means, for example, is that if we have a soliton coming out of this laser that is like 1 picosecond long, we will be here, and basically we can never achieve more than this energy. So in the end, the energy the soliton lasers can emit is actually pretty limited. So it's kind of a bummer because we have this very simple technology with the potential to be very low cost, but it's actually relatively limited, and it didn't really make it into widespread applications such as laser surgery or micro machining or these kind of things that require much larger energies. Then people came up with other ideas, other technologies in mode-lock lasers that basically departed from the soliton field. People started introducing sections with positive dispersion and eventually cavities that were all normal dispersion, and higher energies were achieved, but at the expense of complicating the geometry of the laser and making it less efficient, because since the pulse is actually highly chirped, when it comes out of the pulse, then you need a recompressing stage, and that makes the laser bulkier, but also way more inefficient because you lose a lot of power in that recompressing state at the output. Okay, so this is just as a general introduction of what I'm going to tell you about, and what we will try to solve with the research that I'm going to tell you about is this energy soliton, energy limitation of soliton lasers. So let me just give you a historical perspective of how we got there. So a few years ago, around 2013 or so, we started looking into developing soliton functionality in silicon, right? It's clear that silicon photonics is going to be really interesting and really important. It already is, but it's also clear that trying to achieve nonlinear functionality in silicon, it's important to increase the amount of things that you can do basically in integrated photonics. Now, if we think in solitons in silicon, for example, I wanted to show you with these two equations how things are way more complicated in silicon than they may be, for example, in fibers, right? So this is the nonlinear Schrödinger equation that whose solution, which the solution to this are, it has exact solutions, and these are these solitons that we were talking about. This is how it looks in silicon, right? So the problem in silicon is that other than the negative group velocity dispersion and the Kerr nonlinearity that you need to interact to build your soliton, you have many other things. In particular, you have the two-photon absorption here and the free carrier effects here that basically mess everything up and really like don't allow you to leverage soliton effects and to even sometimes to observe soliton effects. So a few years ago, we started thinking, okay, how can we overcome this, right? So what we did is we said, okay, can we work with silicon waveguides in which we really enhance the role of the group velocity dispersion and of the Kerr nonlinearity, and we kind of try to keep the effects of the two-photon absorption and the free carriers down. So the first thing we did is we said, okay, what is that platform that allows you to achieve the highest level of dispersion and also the highest level of nonlinearity? And what you have here in this graph is basically several platforms that are represented here in terms of the nonlinearity that they can achieve and the beta 2 or group velocity dispersion parameter that they can achieve. And as you can see, photonic crystal waveguides basically blow everything else out of the picture. So what we did is we designed and fabricated a set of like dispersion engineered photonic crystal waveguides, and we started basically just exploring the dispersion relation space to see where we could achieve these effects properly. Now, one would expect, since you actually need a negative and large second order dispersion to achieve solitons, one would expect that, well, first of all, let me just tell you what we're seeing here. We're seeing group index as a function of wavelength, beta 2 as a function of wavelength, beta 3 as a function of wavelength. So second order dispersion, third order dispersion, right? So as I was saying, to achieve solitons, you need a very strong and negative beta 2. So intuitively, you say, okay, let's operate here. This is the level of the largest and more negative beta 2. However, when you operate in that regime, represented by these markers here, you have a problem, and it's that the anomalous dispersion, the negative dispersion, interacts very strongly with the free carrier dispersion, and it actually leads to a new effect that hadn't been reported to that point and wasn't known until that point, which was nonlinear temporal broadening, right? So that means that as you increase the power, your pulse starts to broaden, and this is really not something that was expected, right? We expect that when things propagate in the linear regime, when the powers are relatively low, you expect the pulse to broaden in time because of the dispersion. But at high powers, when the nonlinearity dominates, you don't expect, we didn't expect nonlinear broadening. However, we realized that the anomalous dispersion and the free carrier dispersion can interact to create this nonlinear temporal broadening, and we reported that here. So this was basically messing up our soliton dynamics. So operating here was not the best idea. But something that we discovered in the way as well is that you could use the third order dispersion that occurs at these same wavelengths to actually try to counteract these negative effects and to counteract the nonlinear effects caused by the free carriers. So that was the first time that we started thinking, oh, well, maybe there's something useful about the presence of higher order terms of dispersion, right? But nevertheless, it was not enough to let us observe solitons at these wavelengths here. However, what we did is we started exploring this level here. So one thing that I should have said from the beginning is that the different markers denote the same wavelength, right? So it tells you, for example, this yellow triangle here tells you that you are in a region of strong slow light regime. So the group index is actually quite large. Your beta 2 is still negative, but not as large as before, but still significantly negative. And then your beta 3 here is not very large, okay? So operating at that regime, we actually observe solitons. And this is precisely because the dispersion is negative, but it's still kind of moderate, so it doesn't really interact with the free carrier effects too much to mess things up too much, and then it allows you to see the soliton behavior. And also, the fact that your group index is so large gives you this slow light enhancement of the nonlinearities that even if it also enhances free carriers and two-photon absorption, somehow the scaling of the carrier effect is more beneficial, and it allows you to see solitons at this point. Okay, so we got what we wanted to do. So we managed to find a regime that was kind of ideal to observe solitons in silicon, and we observed shape preserving propagation, and we also observed this soliton compression I was telling you about. But the most interesting thing of this is that it actually opened our eyes to something else. Since we observed that these dispersion curves were so rich and they have so many potential different regimes, we started saying, okay, how about we actually pay attention to even higher orders of dispersion, right? So this shows here, in addition to what I was showing you before, how the fourth order dispersion looks like in this kind of way, right? So at some point we said, okay, here it's actually pretty huge and large, but so let's just do some experiments here. And in principle, since your beta 2 is positive, and we know that we need negative beta 2 to observe solitons, we were not expecting solitons. We really, we were thinking maybe we could get some dispersive waves here, some maybe Cherenkov radiation. We didn't really know what we were looking for, but we decided to do the experiments, and what we saw is that it's actually pretty surprising, but you can get solitons in a regime where beta 2 is positive. And after a lot of analysis, we realized that it's basically because beta 4, a strong negative beta 4 can actually give you the same effect that beta 2 gives you. It can basically generate this interaction with the carrier effect to generate solitons.
Andrea, sorry.
Yep.
Before we proceed, we have a couple of questions. First one is from the chat. So Ivan Sinev asks that recently there was a paper in photonics on gallium phosphide-based integrated circuits, which show much lower two-photon absorption than silicon. Might this platform be better for solitons than silicon?
Yeah, so it's a perfectly valid alternative from solitons. I guess the key is that people want to work in silicon photonics because of all the advantages that you may know. CMOS compatibility, compatibility with the microelectronics as well. So certainly platforms that do not have two-photon absorption and do not have the effect of the free carriers are better for soliton experiments themselves. That's for sure. But you need to kind of solve problems also in the context of the technological challenges and of where the technology is going to.
Okay, so thank you. And another question from Mihail Petrov. Misha?
Sorry, I just unmuted myself. Andrea, just to maybe, we are not that good maybe in math, but can you give some basic or general picture of what you can expect from this fourth power equation? Yeah, so as I can understand, you may have a soliton solution or may not. So what are other things? What is the zoo of the solutions we are facing in experimentally or theoretically?
Right. So first of all, this what we call the biharmonic nonlinear Schrodinger solution, which is basically the Schrodinger equation with, sorry, as a solution I meant equation, which is basically the nonlinear Schrodinger equation with the quartic dispersion rather than the quadratic dispersion. This is, for all we know, a non-integrable system. So it's not going to have exact solutions like the nonlinear Schrodinger equation had. But nevertheless, we've been solving this numerically, and we've obtained these pure-quartic solitons that actually behave I will tell you in a second how they behave. But you can get this soliton or novel solitons type of solution, but then you can also get kind of the same as we were saying before. You can be in a regime in which your pulse broadens if your energy is lower. And then if your energy is higher and the nonlinearities dominate, you can get all kind of the same things that you expected with a nonlinear Schrodinger equation. You can get, I don't want to say the term higher order pure-quartic solitons because we actually don't think that that's quite exact, but you can get soliton compression, you can get soliton fission eventually, and you can get all these things. Does this answer your question? I'm not sure.
Yeah. So as I understand, so this big harmonic nonlinear Schrodinger equation is some kind of a building block of more complicated family of solitons. Yeah, and then what you have, right, which is generalized, you just put a bunch of other terms, and then they mess up.
Yeah, exactly. And that's an important point to remember. Like this is your ideal solution, but experiments are never ideal, right? So you eventually always have something else that is distorted, even in fibers, right? Like, I started simplifying things and saying, oh, in fibers, everything works great. But even in fibers, once you tend to higher frequency, you have Raman effects and things kicking in. Yeah.
Okay, thank you.
Thanks for your question. There's another question. I can answer it. I may answer it since I'm seeing it here, and then I'll move on and give you some more details about these solitons. Do they survive colliding? Well, this is still a work in progress, so I don't want to say too much about it because we're figuring it out. We have done collision experiments with pure-quartic solitons. They behave different than NLS solitons. That's all I can say for now. So I guess asking with respect to your question, they're probably more like solitary waves rather than solitons, but this is still work in progress. It's a good question. Yeah. No worries. So, okay. So just very brief, because I think I'm going a little bit slow. Just to tell you how the experiments look like. First of all, I'm not going to go into details on how we measure things, but just to tell you that measuring things in the time domain at the output of a nanophotonic waveguide is actually quite challenging because you don't really have much energy, so you cannot use your frequency resolve optical gating. You have to resort to some modification of it. But if anybody's interested, I will talk about it at the end. But nevertheless, we obtain a full spectral and temporal characterization of the pulses at the output of our waveguides, including the phase in the temporal domain, as you can see here. And what we saw is something kind of equivalent to what Mollenauer, Stolen, and Gordon saw in the first experiment. So at low powers, we had a little bit of dispersion, so the pulse was a little bit wider than it was at the input. Then as we increased the power to a level in which nonlinearity and dispersion compensate each other, we saw basically that the input and basically didn't change because we were kind of like pumping at almost the exact solution of the solitons. So we got soliton shape preservation, and at higher powers we observed this soliton compression we were talking about. Okay, so everything looks pretty much like the NLS soliton so far. So again, this distortion here is due to the free carriers and so on and so forth. So in principle, we would like to eliminate these, but for now we can live with it. Okay, so they're similar to NLS solitons, but how are they different to NLS solitons? Well, They have a different shape. So for those of you who are familiar with solitons, conventional solitons have a sedge shape in the temporal domain. These pure-quartic solitons have a different shape. But at the beginning, we thought it was kind of Gaussian, and it is kind of Gaussian towards the center of the pulse, but we know now that it's not fully a Gaussian shape. The bandwidth product, the time bandwidth product is also different. But the most important thing is the energy width scaling. And that's when we got really interested about this type of solitons, right? So theoretically, by playing with the biharmonic nonlinear Schrödinger equation, we predicted that the energy of these solitons was going to vary according to this equation. So basically, as you can see here, now we have tau cube in the denominator, right? So if you compare this scaling with 1 over tau cube versus 1 over tau, you can see if we plot it here in the log domain, in the log scale, you can see that for pulses that are short enough, pure-quartic solitons can actually contain much more energy, right? And this is what I'm showing you here for this particular point. This is a pure-quartic soliton, this is an NLS soliton. They have the same width, but they have very different energies, right? So this got us thinking, well, what if we could build a pure-quartic soliton laser that was still quite simple, but didn't have the energy limitations that conventional soliton lasers had? So to do this, to start trying to build a laser, obviously we knew that our silicon photonic crystal waveguides were not ideal. So we started looking for other media with dominant quartic dispersion that were more amenable to build a laser with. First thing that came to mind, photonic crystal fibers, right? Because they also allow you to bend the dispersion quite a bit and to do proper dispersion engineering. We came up with some realistic designs that, we were advised that they could be fabricated. However, when our collaborators tried to fabricate them, they came up with things that were relatively similar to what we asked, but when you measure them, the dispersion is not quite the same. So this is not very fabrication tolerant, and we haven't really achieved successful measurements in this sense yet. So maybe this will work in the future, but for now, it looks like it's pretty hard. The next thing we try is how about we just try to build a laser based on a dispersion managed approach? And what do I mean with this? Well, this is just a conventional soliton laser cavity that performs mode locking via nonlinear polarization rotation here. This is very common in fiber lasers. It has a gain medium here, which is erbium. And the only thing that is different is this spectral pulse shaper. This is a wave shaper that you guys may have in your labs as well. This is just basically something that allows you to apply a phase mask to your pulse, and in this way, basically achieve the dispersion that you want, right? So what you can do with this is, first of all, what I'm showing you here, this is the inherent dispersion in the cavity. So since it's all made out of a single mode standard fiber, you have an inherent quadratic phase induced by propagation in the cavity. So we compensate for this, and we end up with basically a zero net quadratic dispersion. We do a similar thing with the third order dispersion. And what we do is we kind of artificially introduce a very strong negative quartic dispersion, like the one that you see here. And with this, we managed to actually observe the pulse that we wanted to observe. So what I'm going to show you here is these measurements made by postdoctoral fellow Dr. Anton Samusev in Sydney. And what you can see is what happens when your phase mask is off. So this is your conventional fiber laser. This is a soliton laser because, again, you have negative quadratic dispersion in your cavity, and things look very conventional. This is the NLA shape, so you can see it overlaps well with what we are measuring in blue. And this spikes here something called Kelly-Seidman's. I can tell you more about it, but it's basically something that happens when you have a fiber laser, a soliton fiber laser, sorry. But when you turn the phase mask on, when you make the dispersion of your cavity negative and quartic, things change quite a bit. And what you can see here is that we have the pure-quartic soliton shape, the theoretically calculated pure-quartic soliton shape, overlap with the output, and you can see that they match perfectly up to like minus 20 dBs, right? So how about the time domain? Well, again, we measure things in the time domain, and what you see here in blue is the experiment, in red is the expected temporal shape of a pure-quartic soliton, theoretically expected, and in green is the phase. So you can see theory and experiment match perfectly. So we are obtaining pure-quartic solitons at the output, and the phase is relatively flat. So these pulses are almost transform limited at the output. Something that we observe is that when we increase beta 4, obviously, you have a reconfigurable element, right? So you can just change things as you will, and you can control not only, I don't think I have I don't have the spectrum here, but you can see that the spectrum changes. You can see it in the spectrogram here. The spectrum changes, but also the pulse duration changes as you control things with beta 4. But the most interesting thing, and the thing that we were after from the beginning, is to demonstrate this, demonstrate experimentally the energy with the scaling that we were predicting theoretically, right? And this is what we have here. This is energy versus pulse duration. And the markers represent measurements at the output of our laser, and the solid lines represent the energy scales as predicted according to this equation. So each of the subsets is basically a different value of beta 4, right? So if we choose one of them, for example, this is the smaller beta 4 value, what we can see is that basically the different measurements follow this 1 over t cube scaling. And again, this is pretty exciting for us because we think that at least fundamentally we've solved a roadblock in soliton lasers that was really hindering progress in that, and that had kind of like put soliton lasers aside and not made them very interesting for widespread applications. So maybe the vision that Mollenauer and Stolin had when they basically invented the pure-quartic soliton for the first time, this vision of a very simple and very low cost laser could perhaps be attainable now with this. Now, for those of you who know lasers, you will know that these energies are actually pretty bad. You need to pump things up to the nanojoule regime to be interesting. Nevertheless, this was just, this was about the physics. This was about demonstrating a new energy scaling law. And what we have to do now is actually a lot of improvement of the cavity itself, just to try to take this laser technology up to technologically interesting levels. But we have some ideas on how to do that. It's all about improving the cavity itself. And this is just an artist's impression of basically these pure-quartic solitons basically breaking through the barrier of energy with limitation of conventional solitons. Now, one more thing before I move on to finish this part of the talk. Where do we stop? I mean, what is special about quartic dispersion? In principle, they should work for other even orders of dispersion, right? How about sixtic dispersion, octic dispersion, decic dispersion? It should work as well, right? And it does, actually. So what we did is we used our spectral pulse shaper to introduce, instead of quartic dispersion, this beta 6, beta 8, beta 10 type of profile, and we were able to measure pure sextic solitons, pure octic solitons, and pure decic solitons. We showed this in a post-deadline paper in Clio, and what we're doing at the moment is we're trying to measure the energy with the scaling of these cases, which obviously, as you move to higher and higher orders of dispersion, in principle, the energy scaling becomes even more beneficial, right? So the energy scaling of a pure sextic soliton will go with 1 over t to the power of 5, right? And so on and so forth. But things also become more complicated, as you can imagine, as you go to higher orders of dispersion. And I think I'm just gonna skip this and jump to the end of this part 1. And I guess rather than going to the conclusions, maybe I will take your questions. I can see that there are some in the...
Yeah, quite a few of them. So yeah. The first question was from Alexey. Yulin, could you please start, Alexey, if you still have your questions?
Okay, thank you, Anton. Andrea, I'd like to ask a few questions, and the first one probably is a bit technical. Do I understand correctly that in the conservative problem there is a homoclinic trajectory corresponding to the soliton? And if yes, could you please comment how it can possibly be found analytically?
Honestly, no, I can't really comment on that. I'm really not a theorist, and I think any question that I could give you here, any answer that I could give you here will not be as exact as you're looking for. Do you want to try to make that question more in a more phenomenological, from a more phenomenological?
I mean, is this a true localized solution? I understand that the problem is not integrable, but it can still allow for a pure localized nonlinear solution. I'm asking if this is the case.
Yes. So for all we know, yes. So we've solved this equation by using a numerical method that allows us to find a solution that is, if not exact, close to exact. And we've studied the stability of the solution. It's stable to as much as we could test. We actually have a theory paper made by one of our students on this. And so I guess what I'm trying to say is, for all we know, even if this equation is non-integral, these pure-quartic solitons behave phenomenologically as a soliton, really, except for the collision part, which is still unclear.
But the analytical solution is not known.
No, it's not known. We don't have an analytical solution, and it's if there's one, it's going to be complex, because there's quite a bit of oscillations on the tails. Yeah. Yes.
And another question. I think that in this case, third order dispersion and probably fifth order dispersion must be of importance. If you have this soliton with quadratic dispersion, how robust is it against perturbations, say third order dispersion?
I would say it's so far. I would say it's in the same order of magnitude as robust as the NLS soliton.
So you can expect in this case kind of Cherenkov radiation, appearing of radiation tails forming in front or behind the soliton, stuff like that.
Yes, we do expect that, and we've seen signatures of that. We don't, So
probably in the spectrum, probably that stuff in the spectrum was the indication that there are radiating tails.
That there are what? Sorry.
You have shown the spectrum of the soliton, and there are narrow lines in it. Probably it can be considered as the indications.
Yes. You mean these lines here? Do you?
Yes, these lines.
So
probably these lines can be associated with resonances.
Exactly. So you're absolutely right. So this is what is called Kelly sidebands. So basically, this is a resonant interaction of the soliton with the dispersive radiation in the cavity. Yeah, that's absolutely.
And, do you always consider the dissipative terms a small correction? So the main contribution comes from the conservative nonlinearity, and you consider two-photon absorption and stuff like that, amplification and stuff like this as small corrections. Am I right?
Yeah, so in this particular case, since these experiments are done in a fiber laser cavity, we know that we don't have two-photon absorption or free carriers. But for example, for the previous experiments, the initial experiments in silicon waveguides, so these experiments here, basically there was a lot of analysis of turning on and off different terms of the equation, and it was all numerical. So basically split-step solving of the NLS, and just seeing the different influence of the different methods. Yeah, we did that.
Okay, thank you very much.
Alexey, thank you. So I think, Andrea, we don't have to hurry too much, so take your time. We have just quite a few questions. Maxim, I see your hand, but before you, that was the question from Dima Kryzhanovskii.
Yeah, so just kind of technical question. So it looks like that the broadening of the pulse in linear regime is not very big. So like dispersion length is comparable to the propagation length. So like to climb soliton, you need long propagation length.
Yeah, so that's a very fair point. So in this case, I think we had, I think the length of the waveguide was around 3 times the propagation length, I believe. You can check it in this paper here. It was either 2.5 or 3 times. So the propagation length was 2.3 times, 2.5 times to 3 times the quartic dispersion length. Now, you have noticed that very, very good, that it doesn't disperse too much. And is that the quartic dispersion doesn't broaden things as fast as the quadratic dispersion when you are in this regime, in the picosecond regime somehow. So as you know, so well, I don't know if this is widely known or no, but so the characteristic dispersion for quadratic dispersion is, I believe, T, so the pulse duration squared divided by beta 2. In the quartic case, is the pulse duration to the power of 4 divided by beta 4, sorry. So the shorter your pulse, the more influence it has. So for shorter pulses that we also measured, there was more dispersion noticeable at the output of the waveguide. So yeah, this is what I can tell you. So I don't know if you consider that 2 or 3 times the quartic dispersion characteristic length in terms of propagation is enough, but that's what we had in this experiment.
Okay.
Thank you, Dima. Maxim, your turn.
Yeah, thank you, Andrea. So I have maybe a naive question regarding the last part of the talk where you're discussing beating energy bandwidth limit, moving to octic solitons and so on. So it looks like you need a lot of free parameters to kill this beta 3 coefficient, beta 4, and just keep, let's say, beta 10 coefficient. How do you ensure that?
Yeah, so in this case, it's actually relatively easy. So basically, this wave shaper, the way it works is you just tell it, you just program it in MATLAB, and you just say, we want the cavity to have this particular dispersion, right? So okay, let me back up. What you need to do is you need to compensate for the inherent dispersion of the cavity, right? And which is mostly quadratic with a little bit of beta 3, right? So what you do is you can either take the parameters from what the vendors have provided in their data sheets, but what we did as well is we measured it. We have a Luna that allows you to measure the dispersion on a given span quite accurately. So we measure the exact dispersion existing in the cavity, and then we compensate it for it just by applying the opposite to it, basically, right? So with the wave shaper, you can do it pretty easy. And then the residual quartic fifth order, sixth order dispersion that may exist in the cavity is really, really small. So the moment that you introduce a big chunk of it with the wave shaper, you basically, you can basically be sure that you are in the pure sextic soliton regime optic or whatever.
Okay, good, thank you. But so you achieve this functionality only in a limited range of frequencies just because of this tuning of parameters. Okay, thank you.
Yeah, so in this case, you're kind of limited by the bandwidth of this device here somehow. Yeah, right. Which you can, is not fixed. Like this one in particular had a bandwidth, I think, of like 40 nanometers or so, but they made them that are like 200 nanometers in bandwidth. That is basically more than you need, kind of. Yeah.
Great, thanks.
Thank you.
Okay, so it seems we don't have any more questions on this part, so we may want to move on. So again, Andrea, take your time, please.
Okay, thank you. All right, so let's move on and talk about this field of topological quantum photonics. Now, an introduction to topology is something that takes a few hours, well, definitely more than the time that I will have in this presentation. So I guess I'm going to assume that you guys have heard about the field of topological photonics. I know many of you are world experts on this, but I guess I'll just say a few things for those of you that may be less familiar. This is a field that actually comes from condensed matter physics, and it's basically a field of mathematics that deals with quantities that cannot change continuously. They can only change in integer steps, right? So because of this, when you leverage these kind of properties in a lattice, then you can build guidance of light or localization of light that is actually quite robust, because the small perturbations don't bother it somehow, right? So it's a field again that has to do a lot with the band structure, because these topologies, these quantities that are so robust, they exist only in basically the energy band diagram, and that's kind of what relates the two fields here. And for the last few years, we've been looking at how we can actually couple quantum states into these topological modes. And we have been trying to answer, well, does that give us any advantage? Is any of the quantum properties of these states protected by the topology? So that's more or less the high-level introduction of what we've been doing. But maybe I will touch more on how we achieve this particular topology in the geometries that we use for our experiments. So first of all, at a very high level, why are we even interested on studying this? Well, as you know, entanglement is key for quantum computing and quantum information in general, and it's a resource that is leveraged in these fields. There are matter-based approaches to quantum computing, like trapped ions, superconducting qubits, etc. And the biggest problem there is actually what is called quantum decoherence. That basically means that the particles interact with the environment, and as a consequence of that, the quantum state of the particle is basically lost, right? So basically, your computation or whatever operation you wanted to do with that you cannot do it anymore. So in this field, actually, people have been looking at how topology can protect quantum states in condensed matter physics for a long time. And some giants like Microsoft, for example, are actually putting all their efforts in achieving topological quantum computing, which is basically adding robustness to the quantum particles by using topology. And this is also the approach that Nokia Labs is taking in that particular field. But how about the photonics approach to quantum computing? Well, we know that photons do not really interact much with the environment, right? So in principle, photons do not decohere. However, we know that quantum states encoded in photons are actually susceptible to things like backscattering, absorption, phase errors, because your waveguides are wider, your resonators are a little different, etc. Right? So the questions we're asking is, can topology do something to help here or not? So there's been a few groups that I have highlighted here on the right, looking at to answer this question. In this table here, I've tried to gather them all to the best of my knowledge, and this is a table from a recent paper a recent review paper that I published in the field. I'm not going to go into detail through each of them, but you can see that things can actually leverage different geometries from 2D photonic crystal or coupled resonator arrays or even waveguides, which is probably the simplest of them. And this is the approach that I will tell you about in more detail. What's really important here is what is the underlying topological model that supports any kind of topological protection in the structure. In 2D, these approaches are usually based on the quantum Spiel-Hall effect, which is basically something that is insulated in this bulk, and it allows unidirectional propagation on the edges. But this unidirectional propagation is spin dependent, or in the field of photonics, usually we associate polarization with the spin. In 1D, there's usually two models that are widely used, which is the SSH model, which is just exploiting chiral symmetries in the system. And then there's the Andre Harper model, which has been used by some groups as well, which basically, in most cases, it's implemented by modulating the on-site energy of the elements, or for example, the effective index of the waveguides, with a period that is incommensurate with the period of the lattice itself, okay? But perhaps the most important thing to highlight from the different effects is, what are they after? What are they actually trying to protect? What quantum properties are they trying to protect? So for example, the experiments done by Hafezi's group in Maryland are actually trying to see if they can protect spectral correlations, right? So if you use integrated photonic structures to generate correlated photon pairs, can you ensure that they're always going to be generated at the same frequency, right? Even if you have like many elements cascaded and these elements may not be equal to each other. In our experiments, we're actually looking at the protection of path entanglement. So if you encode entangled states across different spatial modes, can you do something to protect this type of entanglement? And then the group of Qian Min Jin in Shanghai is actually doing experiments in terms of protection of polarization entanglement. Okay, so let me just tell you a little bit about the very, very simple structure that we use. We use a silicon photonics implementation of the SSH model. The SSH model was first investigated in 1979 in the context of polyacetylene chains, and then it's been demonstrated in optics in a variety of platforms. Our platform here is silicon photonics platforms. For those of you familiar with silicon photonics, there's nothing exotic about this. So these are silicon waveguides of width 450 nanometers, 220 nanometers in height. The length doesn't really matter too much, but basically silicon on insulator waveguides. And the key here is the alternate size of the gaps, right? So just to put things into a context that may be a little bit more familiar with this. This is an array of equidistant coupled waveguides, right? So if you think of the modes supported by this lattice, as you can see here, this is the propagation constant of each of the modes, of each of the eigenmodes or supermodes of the lattice. You can see that all the modes are extended, right? There's no mode that is in isolation here, which tells you that if you think of where the modal amplitudes are localized here, they're all going to be pretty much extended, right? Spread across the lattice. However, in this case here, as we will see, things are quite different. And we're going to observe something called topological localization. And this is due to basically the topological nature of the lattice. This is very well explained in this paper here by Del Plas, Olmo, and Montenbox. But basically the idea is that when you compute the Zach phase of the wave functions of the band that are below the band gap, you get a different topological invariant for one side of the lattice and the other side of the lattice. And now what you define by each of the sides is a bit relative, but I guess what I want to say is that there's a topological transition between two topologically distinct lattices, and that this interface between the two lattices looks something like this. So it's a long defect. So in principle, just thinking in terms of optics, one wouldn't even expect localization here, right? So you have a lattice and you have a region here that has an effective lower index of refraction, right? So we definitely don't have index localization here. However, as I will show you in a minute, we're going to have a different type of localization that arises from basically the symmetry introduced in this lattice. So let me show you what happens when we transition from this structure to this structure. Let's pay attention at how the propagation constant changes. As we transition from equidistant model to an SSH model, as we alternate the gap, we see that there's a band gap that opens up here. And because we have this long defect in the center, let's see it again, there's a mode that appears here that is completely detached from the rest and that is in the middle of the band gap, right? So this mode is going to be localized along the long defect, but what is special about it is that it's actually quite robust. So what I'm showing you here in the simulation is what happens when you introduce random disorder in the position of the waveguides, right? So if you start, you can do that in your design, right? Like, I mean, you can just go into your design and introduce basically random disorder in the exact position of each of your waveguides in the design, right? So that basically modifies the coupling constant between waveguides. You can see when you do that, the propagation constant of all of the extended modes goes all over the place, but the propagation constant of your topological defect mode remains pinned at the same level. It doesn't change in the presence of this type of disorder. We'll see that there are other types of disorder that can actually affect the structure. So another thing to notice here, and we did this by basically proving the structure by pumping in the center and seeing how the mode looks at the output, is the first thing that you notice, for example, in the power measurements here in this center waveguides, is that there is localization, right? So most of your power actually remains in the center and is exponentially localized. The second thing you can notice is that there's this kind of like zigzag pattern in which basically every other waveguide, you have zero amplitude, right? You can see that being completely true in the simulation case. In the experimental case, there's a tiny bit of residual power here, but that has to do with the fact that we are exciting a little bit other extended modes as well, even if it's kind of like inevitable to, when you pump here in the center, even if your pump couples mostly to the topological mode, is always a little bit of the power is always going to be coupled to extended modes. And that's why you see a little bit of residual power here. But I think virtually we can say that we have zero power every other waveguide. And this is known from for a long time already. This is a strong signature of the topological nature of the mode, the localized mode in the SSH model. So we will use this characteristic to actually this will always kind of like call our attention to the fact that we are seeing a topological mode in our structure. In the case of the equidistant waveguides, there's nothing too special about this. We observed a very well-known phenomenon of discrete diffraction. So when we measure things in the center, we can see that there's no localization here. If we could measure farther out, at some point we will even see higher peaks than this. So basically, there's no localization and nothing special in this structure. Okay. So how can we leverage this to study topological protection of quantum states? Well, we saw that this mode seemed quite stable, at least versus disorder that preserves the chiral symmetry. And we know that silicon is actually a very good platform to basically address, to basically generate quantum states on chip, right? Why? Well, because silicon has a high nonlinear coefficient, and also because these nanowires are actually these silicon waveguides offer very strong confinement. So you can generate with a relatively decent probability correlated photon pairs via the process of 4-wave mixing, which is a chi-3 nonlinear process in which two photons at the pumped frequency give rise to a signal and annihilator photons that are correlated in frequency, because the energy the energy has to be preserved. So basically that means that if you measure the frequency of the signal, that it immediately determines the frequency of the idler, right? Because the 2 times omega pump has to be equal to the sum of the frequencies of the signal and the idler. Okay, so we generate these photons, and we can, just as we did before, kind of engineer our pumping so that we make these photons couple mostly, or this correlated photon pair couple mostly to the topological mode, right? So that is what we did. And at the output, you can just measure signal and annihilator independently. You can just filter them spectrally because they are at different frequencies. And then you can detect them individually using superconducting single photon detectors or whatever you have in your lab. We use superconducting nanowire single photon detectors, and we detected correlations by a time correlation circuit, right? So we know that the 2 photons in a burst were generated at the same time. Okay, so what did we measure at the output? Well, what we measure is what is called the biphoton correlation, which basically tells you where your correlated photon pairs are in the lattice, right? With what probability they are in each of the places, right? So what you have in the vertical axis here is the correlated photon counts. We measure for 2 minutes. And what we have here is the position of the signal annihilator of each correlated pair that was measured in the lattice. So now these labels here just are labeling the number of the waveguides. As you can see here, so waveguide number 0 is the center waveguide in the long defect. And then these are the waveguides to the left, and these are the waveguides to the right. So the first thing you notice is that with high probability, your correlated photon pairs will be in the center waveguide, right? But there's some photons in other even elements of this matrix, right? But what you can notice is that there's 0 amplitude in every other waveguide, okay? And again, that's not obvious to begin with because these waveguides are close to the center waveguide. So in principle, they should, if you don't think in topological terms or in terms of the band structure, you would think that these waveguides here should have more correlated photon pairs than this one, but it's not the case, right? And what you do, what you see when you actually start introducing disorder in the structure, and again, to be clear, the type of disorder that we are inducing here is basically just moving the waveguide around. So introducing disorder in the position of the waveguides or disorder in the gaps, if you want. And we quantify this in terms of what percentage of disorder you're introducing in terms of the coupling constant. This is this 20% here. What we can see is that even in the presence of high levels of disorder, and even if things change in the even elements of the matrix, you keep having zero amplitude in every other waveguide, right? So if you remember what we discussed before, this is related to the underlying nature of the topological mode in the SSH lattice, right? Which had these zeros in every other side, right? And what you can see here is these are the calculations of the lattice in the absence of deliberately introduced disorder and in the presence of different levels of disorder. So you can see that even if the modal amplitude can change in the even elements, it should always remain topologically, because of the topological protection, it should always remain zero in every other waveguide. And that's what we're seeing here. Perhaps what's more important in terms of how useful this may be is the fact that the propagation constant of this mode, of the topological mode, is not supposed to change, right? And that's what you see here for different levels of disorder. Just notice that I have kind of collapsed all the eigenmodes into the same vertical line. So what I'm showing you here is that when we introduce disorder, the band gap closes a little bit, it becomes smaller just because we are randomizing the position of the waveguides, and that leads to not such a clear contrast anymore between the long gaps and the short gaps, or the weak coupling and the strong coupling, right? So the gap is a little bit smaller, but it still exists. But the most important thing is just to notice that the propagation constant remains pinned at the same value. This is normalized to its value. That's why it shows at zero, but it's not really zero. It's whatever propagation constant it actually is. So this was promising, and at least it encouraged us to do more experiments in the field, just to show you that this is actually not obvious and it wouldn't happen in a lattice that is not topological. What we did is we fabricated arrays of equidistant waveguides with a wider waveguide in the center. And what does that give us? Well, this gives us localization. In this case, is just index guiding localization, which is trivial. So we didn't expect anything to be protected here, but we engineered things so that the level of localization was similar to the level of localization that we saw before. So we did the same type of measurements at the output. So we also see that with high probability, the correlated photon pairs will be generated in the center of the defect, which in this case is a wider waveguide. But what we saw is that when we introduce disorder, things vary all over the place. There's nothing that is preserved, no signature that anything is protected here. And again, if we look at the modal amplitude here for different levels of disorder, nothing is supposed to be protected. So no surprises there. And when we look at the propagation constant of this localized mode, we can also see that it goes all over the place when you introduce disorder, okay? So it looks like there's some kind of advantage of using topological waveguiding in topological lattices, and that it can apply, it can have advantages in terms of protecting quantum states. But can we really use it to protect, for example, entangled states, right? And in particular, spatially entangled states. So what we did to try to give an answer to this is we used the previous structure as a building block. So what we did is we built these lattices in which we basically placed long defects, these topological defects, far enough from each other so that they are not basically spatially coupled. And what we did is we introduced entangled states by using a common pump, right? So MLL stands for mode log lasers. I should have probably said that before. So this just emits pulse lasers. It emits pulses. And these pulses will be equally split into the two branches and go into the center of the defects. So we expect the pump to excite the two topological modes, and then we expect our correlated photon pairs to be generated in an entangled state between these two topological modes, okay? So we expect this entangled state to appear in the structure here. This idea of generating entanglement between two spatial modes was actually proposed in this paper here, using also four-wave mixing. They were not looking at topological effects, but basically this, if you're interested on how this entangled state comes about, you can read it here. But basically the idea is that we're gonna have our signal annihilator photons in a superposition of both of them being in mode A and both of them being in mode B, right? And this term here, this phase term here, this psi term, basically determines the difference in phase of the correlated photon pairs propagating in each of the modes, right? So ideally, if both modes have the same propagation constant, that would be 0, right? Okay. So my students went ahead and measured a lot of these type of lattices. I'm showing you here one of them because that's really all you need to see, but the other ones had a very similar behavior. And I've decided to show you a very high level of deliberately introduced disorder so that you see that things work even in very kind of a harsh environments, right? So this is how the biphoton correlation looks at the output of these structures with two topological defects, right? So they have, clearly they show entanglement because your modes, if your signal is measured in mode A, you know that your idler is also measured in mode A, and the same, if your signal is measured in mode B, that determines your idler to be in mode B as well. So there's no cross terms here, for example. That's the first thing you notice. And the second thing you notice is this something that is already quite familiar to us. You observe 0 in every other wavelet. So in principle, this is a strong signature that these modes are topologically protected by the SSH model. So you observe entanglement between two topological modes. So far, that's all we have seen, right? And one thing that you see as well is that even in the presence of very strong level of disorder, experiments and simulation match relatively well. Okay, again, we did the same thing as we did before. We created two defects, but this time just equidistant waveguides with wider, with two wider waveguides. Okay, so this is we're going to create a spatial entanglement here between two modes that are non-topological, that are trivial. Okay, and what we see, and what we saw across many lattices as well, is that there's really nothing that was protected, no spatial feature in the biphoton correlation that was protected against disorder. And what's more, I've decided to show you here 0% deliberately introduced disorder. So this is just the residual disorder in the nanofabrication. It's enough to kind of like mess things up a little bit and deviate from the simulation quite a bit, okay? So we measured entanglement between two trivial modes, and these two trivial modes were not protected against disorder, okay? But to really probe the goodness of these features, we need to actually, to really probe how robust is this topological entanglement, we needed to perform some quantum interference experiments, which we tried to do, but we never really finished because really it's a kind of a complicated task to try to take all these waveguides to interfere with all these waveguides. It's very hard to do, especially in an integrated environment, but we did some simulations that were supposed to answer this question. So what we can see, again, at the output of the lattice, before the interferometer, we have the Newton state that we discussed, signal annihilator in a superposition of being in mode A and B. And after the interferometer, we have two options. We can have the photons split like we're showing here, or we can have the photons bunched. So basically the output is a linear combination of split and bunched states, okay? And to quantify this, we can use the visibility of the quantum interference, which is basically kind of like a normalized contrast between the split and the bunched states. And that depends on this phase term here, on the side term here. So in principle, if the difference between the phase acquired by the propagation in both modes is 0, your visibility will be 1, which is great. But if it's different than 0, then your visibility will be different than 1, and your entangled state will be degraded. So what we did is we did these simulations for different levels of disorder. And what I'm showing you here in the y-axis is the deviation of the visibility, okay? So basically being close to 0 is good because that means that your visibility stays close to 1. So you can see for the topological case, even for high levels of disorder, the mean deviation of the visibility is rather low. But for the trivial case, even for relatively low levels of deliberately introduced disorder, your visibility degrades very, very strongly. So it does look like topology can help protect entangled states on chip. However, how do we move from here to actually solve real problems in quantum computing, and how to integrate these with the approaches that are used now for quantum computing is still to be done. So this is just a proof of principle experiment for the moment. Just this is my last slide. I'm not going to comment much on it. I just want to tell you that these things are quite versatile. So we can start thinking now about creating higher complexity in the entanglement. For example, in this particular structure here, in which we have a short defect rather than a long defect, what we can do is we can generate an entangled state in which our biphotons are in a superposition of 3 different modes. And what's cool about these modes is that one of them is topological and 2 of them are trivial, right? So that allows you to study entanglement between modes that have a different topological nature, which we think is interesting, at least from a fundamental point of view. And you can think of many other things to play with in these lattices. So that takes me to the end of this part 2. So again, I think in the last few years, we've seen that topological photonics is actually moving towards applications. So the field of topological lasers is huge these days, and the field of topological quantum photonics is still starting, but I reckon it has a future as well. People have demonstrated already topological protection of spectral correlation, polarization entanglement, and path entanglement. So it does look like topology can provide advantages here. And then I've told you a little bit about our arrays of silicon waveguides that I think are quite versatile to test topological quantum concepts. And I think that's it. Thank you so much, guys, for your attention.
Thank you very much, Andrea. So we have quite a few questions. The first one was from Ivan Iorsh. Ivan, can you ask it personally?
Yeah, I just I just didn't, probably I'm not getting it correctly. So in the case if we had a single waveguide, in terms of counts, would there be any particular difference? Would be the correlations higher or lower, or they have some different profile? So if we don't have the lattice of a waveguide, but just a single waveguide.
Mm-hmm. Yeah, so this, by the way, this is not that you didn't get it right. This is a common question, and it's a very valid one. Okay, so it's just a different type of scenario. So if you had one waveguide, in principle, your pump will be in just one waveguide. So if you're just thinking in terms of the efficiency of your 4-wave mixing, how many counts, correlated counts you'll have at the output, that would be even better because you really don't have the power split across many waveguides, right?
Mm-hmm.
However, working with lattices it's interesting for many reasons, right? Like, first of all, is the complexity that it allows you to get to, right? So perhaps the first thing to mention in terms of the dimensionality of the Hilbert space, right? Just by by having a higher number of waveguides, the dimensionality of your Hilbert space becomes larger, right? Even if you're still working with biphotons, the dimensionality of your Hilbert space is larger than if you were working with a single waveguide, right? So from a quantum perspective, it's more interesting. But second, having an array of waveguides allows you to have many modes, and these modes can be overlapped with each other or they can be separated with each other, but it basically allows you to introduce more complexity in the modes. Yeah, I don't know if that answers your question. It's just a different scenario. Now, if your question is, I don't know, maybe this was not your question, but a question that I get a lot is that basically the question that everybody wants to ask is that does this solve backscattering, right? Which is the biggest problem that is solving photonics, right? Because in a single waveguide you would have backscattering, and in a in a lattice, you will have backscattering as well, right?
Well,
No.
I assume no. No, I know the answer for that.
Yeah. So my point is, this doesn't really solve this issue. This is not really not breaking time reversal symmetry. This is really not going to give you protection against backscattering, which is kind of like the holy grail of topological photonics that nobody has demonstrated yet in the whole field.
Okay, thank you. Thank you.
Thank you. Maxim, Nikita, I see you. Just a second. I also had a very short question, but I'm not able to raise the hand since I'm an organizer. So my very simple question is the following. You've shown that your disorder does not affect the spectral position of your this topologically protected mode. I'm wondering what this frequency depends on. So probably it may depend on the average period or something of the system. And I wonder whether so you have introduced just arbitrary disorder or a very special type of the disorder preserving this period.
Yeah, so more than the period itself, one of the things that determines the value of the propagation constant of that mode is also the width of the waveguides. Okay, right? That's basically the propagation constant of each of the individual waveguides as well, right? That plays a role in moving things up and down, right? In that diagram, if that makes sense. Now, this is structure, and the SSH doesn't give you protection against what we call on-diagonal disorder, which is exactly that, right? So if your waveguides start to vary in width widely, there's nothing that the SSH can do for you, okay? Having said that, one thing that we observed in our experiments, and this is not maybe it's not because of the fundamental protection of the topological SSH waveguide, but we did observe that the topological localization was more robust to width changes than the trivial localization. I don't know if this is a fair comparison or not, but this is something we did observe in the experiments. Yeah.
Okay, thank you very much. I see. So probably next one was Maxim Gorlach.
Thank you, Andrea, for the fantastic talk. And actually, even though I'm constantly advertising this activity with topological protection of quantum light, maybe I have to ask a bit nasty question now. So you demonstrate robustness of path entanglement. And then I wonder whether it is related to the topological protection, the topological nature of the used model, or rather to the some specific pattern of the state which you are exploiting. For instance, imagine I'm designing some trivial model, but I have a bandgap and I have some defect state inside the bandgap, and it is characterized by some unique pattern of a single photon probability distribution. Then I believe I will receive very similar picture of the two photon path correlations. So could you comment please on that?
Yeah, so that's a good point, right? So just by having a large bandgap and a mode isolated in that bandgap, you're going to obtain, yeah, that mode is going to be a little bit kind of untouchable, right? Because your bandgap is very large. So in terms of having like some spatial features of the biphoton correlation being preserved against disorder, you may get something. I don't know exactly what you're envisioning, but it may be possible. What I don't think it'd be so much possible is just to keep the propagation constant of that mode fixed. I think that is directly related to the topological protection in the SSH model. But
yes, exactly. But yeah, it is preserved only under some class of perturbations. Once you start to change, let's say, the width of the waveguides, then it's all gone.
Yeah, that's very true. Yeah. No, I fully agree with you.
Yeah, and then the second question may be like a perspective. So I can see that here the topological protection of biphoton correlation originates from the topological nature of the underlying single particle model. And I'm wondering, it could be an interesting question maybe for future, for all of us, whether we can realize some system which is topologically trivial for single particle case, but then still it still provides some topological protection of biphoton correlation. That would be maybe some interesting fundamental question. What do you think on that?
So you're talking about the underlying structure being trivial?
Yes, yes, but still.
But manifesting in a topological way in the quantum domain somehow, right?
In the quantum two-particle domain, yes.
Mm-hmm. I think, I mean, at this point, this is kind of a hypothetical question, but I don't think it's a crazy idea, because the truth is that there's a difference. I mean, it's not that everything translates directly from the classical domain to the quantum domain, right? So there's new rules that the topology sets also in the generation of these quantum states. So it's possible that you can play with things in a way that your pump is not topologically protected, but your photons are. And that reminds me of something that we saw in this model. And I haven't really talked much about it at all, but since I think it can be relevant to your question. This is, to me, one of the cutest experiments we've done in this regard, and one of the most interesting experiments we've done, although maybe the use is not so clear, but it's, I think, related directly to what you're asking. When you input your pump in the center here, because of the symmetries of the system, your pump couples only to the trivial modes, right? So there's three modes here that are localized kind of close to this short-short defect. There's a topological mode and two trivial modes. But because of the symmetries, when you pump in the center, you only excite the trivial modes, nothing topological, not about the pump. However, when you look at the generation of the photon pairs can actually get generated in the trivial mode, sorry, in the topological mode. So whereas your pump was just in exciting a beating pattern between the trivial modes, your topological, your quantum state is in a superposition of a topological and trivial modes. So I think that's related to what you were asking.
Yeah, that's interesting. We'll be happy to see the preprint then.
Yeah, we're going a bit slow on this because basically I left Sydney, and now the communication with the students is not as easy. The students are also, they moved on to other things, but yeah, I'm also really excited about publishing this and seeing and just getting feedback from people like you, really, and seeing where we can take this.
Thank you so much.
Yeah.
Thank you, Maxim. Nikita?
Andrea, thank you for a great talk. I have a couple of questions. So let's start from slide 13.
Slide 13. So 13 as in like the soliton stuff?
No, 30.
Ah, 13, sorry. Okay.
Okay, so you consider here the generation of entangled pairs via spontaneous four-wave mixing.
Mm-hmm.
Pair-free process, which is very weak. So have you or maybe somebody else considered generation via SPDC in, say, 3-5 alloys like gallium arsenide, which are also technological, but it's a Chi2 process and it's very much strong.
Yeah, absolutely. So the group of Chiamin Jin, I'll show you the reference here if I can. Where is this? The group in Shanghai has been looking at this. I think it's in borosilicate waveguides, but there's a lag between my thing. But yes, people have looked at this in the context of polarization entanglement. And I'm sorry that I can't find the, where do I have this? Let me just get out of this. There we go. There we go, here. So if you're interested, yeah, so this bunch of works here in this table, you have it separated by the way in which people generate the quantum state. And these 4 works here use SPDC.
Okay, and also about the disorder. So as I understand, you have considered only positional disorder. So have you considered the disorder in waveguide web?
Yeah, so we have considered it, and yes, as I mentioned, the SSH doesn't give you fundamental protection against that, because that's if you think of the Hamiltonian, right? So that would be on diagonal disorder rather than off diagonal disorder, right? So So the SSH gives you protection against any kind of disorder that basically preserves the chirality of the symmetry, right? Because it's the chirality, the chiral symmetry that is actually giving you the protection, right? But the moment you start playing with the widths, then the SSH doesn't give you protection anymore. The way we get around it is that actually this is not a hugely significant effect when you do these experiments. So even if you do have some fabrication tolerances, they don't seem to affect the big picture somehow. But we do very clearly admit that this doesn't protect you, again, at least at the fundamental level, it doesn't protect you from disorder in the widths. Yeah. Yeah. If you're interested, I think in this paper here, I'm not sure if in the end we put it in the supplementary information, but we have a specific analysis of how the width affects the model, and yeah, and we comment on all this.
Yes, thanks. Also about the state, have you considered how other free Bell states, except this null state, change?
I'm sorry, can you repeat the question?
Have you considered the other free Bell states, except the null state, which is really...
Oh, yeah, absolutely. Yes, we haven't considered it, but you could, and that's kind of what I was hinting at the end. Like, you can just start playing with different modes and just like, you know, just input, just playing with your pump, so that then your correlated photon pairs couple to an arbitrarily large number of modes. Yeah, but we haven't. This is all we've looked at in this domain.
Okay, thank you.
Thank you.
Colleagues, do we have any questions? More? We had quite a few already, and it's 1.5 hours we are online. So I think it is more or less it is what we wanted to ask. So I would like, Andrea, I would like to thank you for accepting our invitation and giving a brilliant talk on our seminar. So you see there were many questions and discussions here. It's always very good. And before I finish, I just wanted to make a small announcement. So the next optical seminar will be given next Friday. It will be Professor Vladimir Drachov from Skolkovo, and he will be talking about metal nanoparticles. So see the schedule, please. So I would like to thank everyone for joining this seminar. So very soon the video will be available at our YouTube channel. Please join it. Stay safe and good luck to everyone.
Thank you, everybody. It was great talking to you. Thank you.
Thank you very much, Andrea.
Thank you, Andrea.
Thank you. Take care, guys.
Take care and hope to see you soon at some
And then we have a free discussion, of course.
Likewise, guys. See you soon.
Bye-bye. Bye.